Oh, okay. Also, I forgot to put in the post for attendance this morning. I'll edit after the class nanti, after the lecture. All right. Let me share my screen. Okay. So everybody can see the slides, yeah? Alright. So if I get disconnected, kalau saya putus tiba-tiba, please WhatsApp me, ya. Sometimes this laptop is a little bit has a little bit of a problem lah. But hopefully everything goes well. So let's see, where did we stop? Okay, we were looking at stratigraphic categories, and we stopped at lithostratigraphy, right? Okay, we looked at the problems with lithostratigraphy. All right. So the problem with lithostratigraphy is just connecting and mapping based on rock type, sandstone with sandstone, limestone with limestone, and so on. Okay, so that is lithostratigraphy. It is a very useful tool. It has been used for a long time. Okay, kita dah guna lama kaedah ni. So you go to a location, let's say Perlis here, and you just map out the different types of rock, right? And sometimes you can also arrange it based on relative age lah. You have older carbonates and younger carbonates and so on. All right. Now the problem with lithostratigraphy is it does not provide us an accurate picture of Earth history. Okay. It's very useful for practical reasons for exploring and managing Earth resources, minerals, hydrocarbons, water, and other things, right? But if you want to really know the relationship between different units, you need to think about time. And the problem with lithostratigraphy, it takes out Walther's law. Okay. So I think everybody knows what Walther's law is, right? Now, the lithostratigraphic concept is like this, right? You have sedimentary rock layers laid horizontally, they are stacked vertically on top of each other. Then you can divide your sedimentary succession into units based on lithology. A is limestone, B is older mudstone, C is sandstone, there's a younger mudstone at the top, we call it unit D. Maybe you can give it a name like a formation or a member and so on, right? Like we discussed before. All right, this works only if the Earth was simple. You have one layer of sandstone during one single period of time, and it goes around the world. That does not happen, right? This is reality. It is more like this, right? Physical and chemical characteristics are not uniform for units of large areal extent. You can trace a sandstone layer, let's say for, ikut sini kan, for 5 meters ke, and still sandstone. But you walk further along the surface, tens of kilometers, hundreds of kilometers, you'll notice that the fascies change, even in the single layer, right? And that is because of Walther's law. Okay, so just a recap, what is Walther's law? Walther's law states that fascies adjacent to one another in a continuous vertical sequence were adjacent to one another laterally. It just means this. If you have a surface in a single point of time, you take a snapshot, an aerial view, you'll see that the environment changes laterally. Maybe you're standing here, right, on the shoreline. For the landward, it is swamp and floodplain. For the seaward, it is beach followed by shelf, right? But all of this was deposited in a single time, right? So the fascies change laterally. Okay, and what you get laterally is also what you get vertically because the fascies also stack on top of each other with time. Why? We'll talk about that later. Okay. So each different depositional environment will have a different fascies, and your fascies will change laterally. Okay. So yeah, lithostratigraphy is useful, but we need other tools. One of the other useful tools for mapping and connecting rock layers are fossils. Okay, and to use that, we need to learn another principle, and you might also have learned this in other lectures. This is the principle of faunal succession. Okay. Now, if you've gone to an outcrop, lots of outcrops, you will notice that different layers can contain different kinds of fossils. Right? You go to Langkawi, I find trilobites at Gunung Mat Cincang, or I find dinosaur bones in Pahang, right? I see these lots of these elephant fossils in the Gopeng area inside the caves, right? So different kinds of rocks can have different kinds of fossils, and if you look at a lot of rocks throughout the world, you notice that there are patterns, right? Older rocks tend to have one type of fossil assemblage. Younger rocks have a different type of fossil assemblage, and there is actually a pattern to it. Biota, meaning life, have followed one another in an orderly succession through geologic time, and each different layer contains its own distinct fossil assemblage. It is unique to the layers. Okay, and because of this, you can actually use fossils to determine the age of rocks. But this is relative dating. Yeah. Okay, so there's going to be a certain arrangement. Let's say for location 1 here, right, you have these 3 ridges here, and they are disconnected by canyons in between. And you want to connect the layers between them. You know that once they were continuous, you could actually trace them. You should, based on the basic principles of stratigraphy. Layers were deposited horizontal, and layers were laterally extensive. So you sepatutnya boleh trace here. And if you study the fossils from locality 1 sini, you notice that there is a pattern. In this second layer, which I call B, I find this trilobite. In C, overlying it, I find this kind of fossil, and D, this kind of fossil, and this kind of fossil. And they don't mix with each other, right, in this case. So then you go to the next ridge here, you see the same kind of pattern. This one must be the same age because it has the same fossil. And this one can be correlated to this one unit can be correlated to this unit, and so on. And you can go do it for the next outcrop. For the next outcrop, you can even do it for the whole world. Okay? Okay, so you're doing correlation using fossils. Okay? So yeah, fossils are most often used in correlation to establish a time equivalency between strata. Fossils have proved to be the only the only widely applicable tool of time correlation in sedimentary rocks. It's the most popular way to do it. It's the easiest way to date your rocks. Okay, you can use radiometric dating, but that is time intensive. You have to go to the lab and so on. It's also expensive. You need to have money to do it, right? Fossils are very easy. You can go to the field, collect it. You can go to the literature, compare it with other parts of the world, and you can have a rough correlation and date. Okay, especially useful are what we call index fossils. These are unique fossils that tell you really constrains the age of the rocks. Okay? They can be very useful markers for geologic age. Okay. So far, any questions? Clear?
Clear.
Clear, sir.
All right. Okay, so you can correlate using fossils, right? Now, the best thing in using fossils is sometimes you get these fossils which kita panggil dia fasces independent. Dia bebas daripada fasces. Let's say this coil fossil here at the top in area A, right? Maybe it's an ammonoid. Let's say it's an ammonoid. Yeah. Now in area B, you get the same thing. But notice that the fasces is very different. Here it is sandstone, but here it is mudstone. That is what we mean by fasces independent. It doesn't care what kind of substrate is at the bottom because it is a swimming animal, right? So correlation is now not based on lithostratigraphy. If we just use simple lithostratigraphy, you make mistakes. Macam gini, sandstone, I connect with this lower part, but you will be wrong. It's not the same age. So be careful with just using lithostratigraphy. Okay, so using lithostratigraphy tadi, when we use lithostratigraphy, you have sedimentary rock succession where you divide it into formations, right? Okay, so just give names gitu. But when you use biostratigraphy, use fossils, you try to plot out the vertical range of your fossils. Okay, so this is a sedimentary succession here, the log. This is a sedimentary log on the left hand side here. Limestone, mudstone, and so on, lots of different kinds of rocks here. Then you plot the different types of fossil taxa here. So you have genus and species in here. Everybody's gone through the fossil lectures, right? And you can divide your sedimentary succession into zones based on the fossil range. Okay, so you are dividing up the rocks stratigraphically based on fossil content. Index fossils are used to characterize the rocks into zones. One thing you need to remember, good index fossils must be abundant and have short time ranges. Right? Things like graptolites, conodonts, fossil pollen, palynology, foraminifera are very useful for dating rocks because they are abundant. They live in marine environments. They tend to be planktonic or pelagic, and so they can move around everywhere. They're found globally. Okay, but they evolve very rapidly. So maybe one genus is only restricted to just a few million years. Yeah, so very useful for dating rocks. Okay. Okay, so this one, this is just an example of correlation between different parts of the world. So in this case, this is a combination of lithostratigraphy and biostratigraphy, right? So these are several sedimentary logs on different parts of Southeast Asia, from Peninsula Malaysia here, Perak, Perlis. Then you go up to northern Thailand, southern Thailand, Satun, northern Thailand to East Myanmar and South China, right? So using lithostratigraphy, you can already see a pattern. Oh, the older rocks here, Silurian here, limestone. So I can trace them very easily. And even now, in the middle here, the Devonian rocks are also easy to map. Oh, same thing, black shales, sandstone, followed by mudstone, then capped by limestone. So general pattern is there. You can use lithostratigraphy. But when you go to the finer details, you have to be very careful. Yeah. Sebab sini ada different sikit. So you go from mudstone here and then it goes into limestone here. So you need to use fossils, the same kinds of fossils, to make a really good correlation. So you combine litho and bio. Okay, so different rocks are confined to rocks of different ages. However, dating using fossils ni kena ingat is what we say relative dating. We can say if a bed is older or younger. That is all we can say using rock fossils. I have trilobites. These are the oldest rocks. here, let's say with fossils, right? But that is all I can say before the advent of radiometric dating. That is all I can say. I can just say older and younger, right? Okay. But so that has been a problem for a long time in geology. Lama dulu. We cannot really put numbers. People say, oh, you know that it's old, but how old? Cannot really say during that time. Okay. So we need a method to accurately measure the age. And so that is where radiometric dating comes from. Okay, so dating using fossils is relative dating, secara relative. We're just comparing, kita banding, okay? Younger and older. The actual of the age of the rocks, you can use what is called absolute dating. Okay, and this gives you numbers. It's based on the radioactive decay of minerals. You've learned this in sedimentary school dulu, in matriculation kan. You learn about radioactive decay, right, of minerals. Okay, so just a little bit, a bit of recap here. You all know this already, but just saya repeat sikit je lah kan. So we know that you have elements making up material in the universe, right? And elements may exist in different isotopes, right? So different isotopes of an element have different numbers of neutrons in the nucleus. Okay, so we call these nuclides. Some of these nuclides are unstable, will change from one nuclide to another. And this process is called radioactive decay. Okay, dia reput. Right? Now, what is interesting about radioactive decay is the rate of decay is constant. Dia reput dengan kadar yang tetap. Kan? So, the rate is constant. The decay is constant. And you can measure how much nuclides change into another daughter nuclide, right? So basically, you can use these decaying nuclides as a clock. You boleh guna sebagai jam because of the rate of the constant rate of decay, right? The collection of atoms of a radioactive nuclide decays exponentially at a certain rate. This is called the half-life. Okay. After one half-life has elapsed, one half of the atoms of the nuclide will have decayed into a daughter nuclide. Okay. So let's say we have an unstable nuclide here. Now, if you look at your mineral there, it's 100% made up of that nuclide. But after a certain amount of time, that amount reduces to half, 50%. Okay, that's changed to another nuclide. Now this increases now, so it becomes half of the material. Okay? So this amount of time is called the half-life. So after the same amount of time, after this, time number 2, half of this also changes to the daughter nuclide. And so on, and so on, and so on, okay? The rate is constant. You can use it as a clock. So yeah, radiometric dating is a technique used to date materials such as rocks, usually based on a comparison between the observed abundance of a naturally occurring radioactive isotope and its decaying product. Yeah? So example here bawah ni lah ya. 100 units of uranium-235 will become 50 units of uranium-235 and 50 units of lead, plumbum-207, after a half-life. But in the case of a half-life, uranium-235, it is 0.7 billion years, 700 million years. So you have lots of different kinds of isotopes, and they have different rates of decay, different half-life. So these are some of the isotopes used for radiometric dating. Uranium to lead, biasanya, calcium argon, rubidium to strontium. Okay, this can be used. Let's notice the half-life: 4.5 billion, 700 million, 1 billion, and so on. Kan? So this can be used to age really old rocks. Okay, and where do you find these kinds of nuclides? Inside minerals such as zircon, okay, muscovite, biotite, hornblende, volcanic rock. Okay, so a lot of it is coming from igneous rock. Okay. In the news, you hear a lot about carbon dating, right? This is also radiometric dating, but in geology we don't usually use it lah. This is more for younger rocks, younger sediments. Well, sorry, younger sediments lah. Talking about material which has carbon lah. Sorry wood, charcoal, peat semua there, and bone organic material. So notice the half-life for carbon-14. That's the scale of just centuries to millennia. It's too short a time to date rocks. Okay. But if you're interested in the quaternary, it's a very useful tool. Okay, so that's lithostratigraphy first. Then you have biostratigraphy. Then you have radiometric dating, right? Now you combine all of these tools together, it's going to be a very, very powerful thing. You come up with chronostratigraphy, where you combine relative dating and absolute dating. So far, okay, tak putus,
Okay, Doktor. Okay lagi.
Okay. Okay, so let's see how we actually use this, right? How do we do dating of the sedimentary successions? Okay, so we have a stratigraphic section along the left-hand side of the slide here, ni kan? So this guy has already logged a section, an exposed section, and he has a relatively good idea of what happened in the history of the area he or she is working on. So you have older rocks at the bottom and younger rocks at the top. And based on the lithology and the fossil composition, you can come up with a story. The oldest rocks below here tells you that there was mud deposition, but there was no fossils. This was followed by a younger period where you have mud deposition and you have the occurrence of fossil A. Okay. Then you have another period here, mud deposition, followed by a layer of volcanic ash because there was a volcanic eruption. Then followed by more mud deposition, then the occurrence of fossil B here, more mud deposition, another volcanic eruption, and then followed by more mud deposition. So that is already a story. Okay? Now the problem again, the story does not have any dates. It's just a relative dating. Now this is where the volcanic ash comes into the story here. Okay, so volcanic ash can have minerals, and some of them have these minerals can contain radioactive elements, right? And they can decay, right, into daughter nuclides. So you can actually date these using radiometric dating. Okay, so let's say we date this volcanic ash in the bottom here, above the fossil A unit here, to 151 million years. Okay, there's an error bar, plus or minus 2. It's not, So there's a little bit of uncertainty here about the age. Maybe it's 151, 152, 153, and so on. There's an error there. Then you date the younger ash layer at the top here, and goes to 140, plus or minus 3 million years old. Okay, so now we have a more accurate story. The rocks below the volcanic ash must be older than 150 million years. The rocks above the second ash layer must be younger than 140 million years. The rocks in between the two layers is between 151 to 140 million years old. So we have a better story now. before older than 151 million years ago, mud deposition was dominant in the basin, and you had these marine fossils occurring. Then you had a volcanic eruption 151 million years ago, and this was followed by mud deposition, and also another kind of fossil occurred. So we have a better story now. Okay. Then once you have that, you can compare the fossils here to other parts of the world and see if you can correlate. And you can do this for the whole world. Okay. So far, so good, eh?
Okay there.
All right. So you can divide. Okay. This is just terminology, but this is more on than paleontology, and I think you already gone through these slides in paleontology. So you can divide your sedimentary succession in what we call into chronostratigraphic units: era, time, system, series, and stage. We're not going to learn this in this course. This is for other courses. Okay. Oh, where was I? Yeah. Okay. So you have what we call chronostratigraphic units, and we use the term era, time, system, series, and stage. A chronostratigraphic unit is the rock strata deposited within a particular geologic time. And then you have what we call a geochronologic unit, and these are your eras, periods, epochs, and age. Okay, this is geologic time. This is position of the rock strata, which is chronostratigraphic units. So, for example, rocks of the Cambrian system is called a chronostratigraphic unit, and then you have what is called in terms of time a geochronologic unit is called the Cambrian period. These are two different things. Yeah, these we are talking about the rocks, Cambrian system. These we are talking about the time, Cambrian period. Time and the actual rocks are two different things. So sometimes when you read books or papers, you notice, lower Miocene. What's the difference between lower Miocene and early Miocene? Yeah? Well, one is chronostratigraphic, one is geochronologic. Yeah? Lower, middle, upper is used for units, chronostratigraphic units. When you go to you have a sedimentary log, and you say this part here is lower Devonian, this one is middle Devonian. But we're talking about age. The age is early Devonian and middle Devonian and late Devonian and so on. Okay, so you combine all of these together, you get the geologic time scale. Yeah. Early geologists recognized that there was an order to the rock record, right? You can arrange your layers from older to younger using lithostratigraphy. Then you find that different layers have different fossils, right? And then you can arrange based on the fossil content also. And then you also can date the rocks using radiometric dating. Okay, so you have lots of people throughout the whole world working together to organize all these various layers throughout the whole world to come up with a history of the Earth. Okay, so stratigraphic studies from the 17th to the present 17th century to the present day have resulted in a standard geologic time scale, which is a time scale, and it is divided into geochronologic units. So you have larger units here, eons, for larger scale units. Then your eons can be divided into eras, and your eras can be divided into periods, and some of the periods can also be divided into smaller epochs, and so on. Yeah. Okay. Yeah, here you have. So let's say, for example, here the Paleozoic is made up of several periods: Cambrian period, Ordovician, Silurian, and so on. Right. And the Paleozoic is part of the eon called Phanerozoic. Okay. And based on the work of all these stratigraphers, lithostratigraphers, biostratigraphers, chronostratigraphers, this is the result that we get. Okay? The geologic time scale. This is the international stratigraphic chart. And it is a combination of, you have your periods, eons, and epochs on the side. Here, you have radiometric dating here. And this is based on correlation of lots of sections throughout the whole world. Thousands of people working together. Okay. Okay, so I think that's it for the lecture. Any questions? Okay. If there are no questions, let's have a. It's 8:37. I'll give you a 5-minute break, and I'm going to upload the practical for today. Then we can start with the first practical.
Okay, Doctor.